Hello and welcome. Thank you for joining our webinar. Today's topic is EMF-Aware planning of 5G network rollouts. IXUS is a software solution that can be utilized to ensure mobile base stations are EMF compliant. For more information on IXUS, head over to ixusapp.com or email us at info@ixusapp.com. In this webinar, we will introduce ourselves and explain how we fit into the world of RF safety compliance. We'll discuss the misinformation spread around and how that influences the telecom industry. We'll have a look at the features of 5G, especially those that influence the RF compliance status of mobile base stations. Exposure-aware design is a term we use for planning sites that wouldn't come around and haunt you later. We'll have a look at how easy it can be if you have the correct tools. We'll briefly explain our antenna modeling process, followed by some real-life examples. A product called IXUS is part of a South African technology investment group called AlphaWave. This group consists of a number of subsidiaries and products. AlphaWave is a specialized technology investment group with exceptional domain expertise in machine learning, data science, software development, extended virtual and augmented reality, artificial intelligence, but more importantly, electromagnetic fields. The core of this group was initially established in the 1990s with its main focus on computational electromagnetics. The flagship product called FECO, published by our company, was later sold to Altair. IXUS was designed from around 2005 onwards out of necessity for an efficient, easy to use and accurate solution. The first commercial version of the software was released in 2009 after being used internally for a few years. Today, IXUS is a globally accepted solution for ensuring RF compliance. Our head office is located in Cape Town, South Africa, and we have offices and partners in the USA, Canada, Europe, Malaysia, and Australia. We have clients ranging from mobile operators to manufacturers and consulting firms all over the world. The 5G infodemic. The debate on health concerns related to electromagnetic field exposure has been ongoing through every generation of mobile technology. According to the WHO, an infodemic is an overabundance of wrong information deliberately circulated to advance alternative agendas. Mis- and disinformation can be harmful to people's physical health, and today, a large number of people are concerned about potential health impacts from being overexposed by 5G radio frequency emissions. Fake theories and misinformation about 5G features causes a challenge to manufacturers and operators of communication systems. In February last year, the WHO stated, and I quote, "To date, and after much research performed, no adverse health effects has been causally linked with exposure to wireless technologies, provided that the overall exposure remains below international guidelines. No consequences for public health are anticipated." The features of 5G. In terms of RF compliance, the features included in the 5th generation release that are worth mentioning are beamforming, densification, and the use of so-called millimeter wave frequencies. Millimeter waves are electromagnetic waves typically defined to lie within the frequency range of 30 to 300 GHz. In the telecoms industry, the entire band from 8 GHz upwards are generally referred to as millimeter waves. First, second, and third generations all operated roughly below 2 gig. 4G included some higher frequencies in the centimeter wave band. 5G equipment can operate in frequencies mobile networks couldn't previously. Luckily, ICNIRP and other guidelines are all up to 300 GHz. For RF compliance on mobile base station sites, this is nothing new since most of the transmission antennas already use this band. Our tool has more than 500 antennas in this higher band already. The second feature on our list is cell densification. From an RF compliance point of view, this means more sites equals more work, smaller installations, and the actual antennas are usually closer to the general public. This is no problem because we can do our simulations on a very small scale. The only feature of 5G that causes significant problems for RF compliance is beamforming. To explain this, on the left, you have a single pencil beam, like that of a 5G beamforming antenna array pointing all the power to one user. But we don't know where this beam is pointing, and thus all possible scenarios have to be considered. This is shown as an envelope on the right. At IXUS, we have an antenna service providing models of the highest possible quality. We have a team of antenna engineers specialized in the creation of antenna models. We use data sheets, pattern files, or any available information. Antenna models are reviewed and verified using a formal traceable process. Every version of our antennas published to our antenna database has a verification document available. "5G antenna modeling has received special attention the last few years to ensure we captured the dynamic beamforming nature of these antennas accurately. Our IXUS antenna engineers use traffic envelope data patterns obtained from manufacturers together with a ray tracing approach to produce a model that accurately captures the beamforming nature, as shown on the bottom right. Something to note here is that we can also model a particular beam set or configuration of the 5G antenna if needed. Incorporating specific power scaling settings is possible, and an example will be shown later on. Exposure-aware design. How do you make sure your future sites are compliant? You add the compliance step into your workflow and as early as possible. If you are responsible for the compliance of the base station, you need to make sure that you gather enough information early on. What is the most important thing to remember when planning where to install your 5G antennas? We recommend that you don't intrinsically assume that your base station would be compliant when installing beamforming antennas at the same height as other antennas, especially if the zones were already close to being over the limit. In order to explain why this is important, first you need to understand one basic concept in IXUS. The ICNIRP guidelines, FCC OET 65, Safety Code 6, and most other guidelines have two limits. The ICNIRP guidelines refers to general public and occupational limits. In our 3D representations of these limits, or hazard zones, we use two main colors, yellow and red. Yellow equals 100% of the general public exclusion zone limit. Red equals 100% of the occupational exclusion zone limit. Consider a tri-band panel antenna. We can see from different angles where the problematic areas are. The public RF hazard zone extends out several meters in front of the antenna and extends much further than the occupational hazard zone. For the current input power, we see that the lowest point of the zone is 0.7 meters, or just over 2 feet, below the bottom of the antenna radome. Next, we look at a pentaband panel antenna with standard input power. This time the lowest point is 1.25 meter, or 4 feet below the bottom of the radome, as indicated. When we consider the beamforming antenna, also with standard input power, the lowest point of our zone is over 4 meters, or 13 feet below the bottom of the radome. This is due to the vertical scanning beam steering capabilities of most 5G antennas.
Let's look at an example. So consider a pole-mounted installation with a single panel antenna, a very small little base station. The spatially averaged values at the accessible area where the person is standing was calculated. The maximum is found to be 4.841% of the public limits. So this is with only the 4G antenna.
When we add the 5G antenna on the same bracket, right next to the 4G antenna, we suddenly have a problem. Now the spatially averaged values are well over the public limits. This is a very conservative simulation, which can be modified in IXUS to accommodate duty cycle, load variation, and other factors to decrease the actual EIRP. In this case, the power levels of the 5G antenna is just 25% of the previous slide, which might represent the inclusion of a duty cycle associated with duplexing technology such as DDD. The maximum spatially averaged value is now much lower at just 33.52%. Depending on your local compliance rules, this should be labeled as compliant. For this, let's call it more realistic example. To see the influence the 5G antenna has on the zone, you have to see the side view. As indicated here, the area of concern is close to the antenna, reaching much lower than the non-beamforming models. Case studies and examples. In order to really understand the value of this tool, it makes the most sense to see what it can do in real life. We'll look at a rooftop site with a very obvious problem. Then we'll show some examples of small cell sites. Thereafter, we will show you a practical example and demo of how the tool is used for a problematic tower. This first example very clearly shows that installing your 5G antennas at the same height as your current antennas is usually a bad idea. You can clearly see that the percentage of the standard is exceeded where the public has access. In this specific case, the site had to be powered down and the antennas had to be moved. If the radio planner had spent a small amount of effort using our tool, this would never have happened. Because this was a problem linked to the rollout project, the funds for resolving the issue had to come from capital expenditure. Luckily, moving the antenna higher up on the same offset bracket was all that was needed. But going over budget on a site like this can easily be avoided. This might not be your standard small cell, but in some countries this is regarded as a small cell base station site. We mentioned densification earlier. This is to show that smaller base station antennas can be simulated in IXUS with no issues. In our view, the term small cell refers to single sector sites with less transmitted power. On the left, you'll see some smaller installations using omnidirectional antennas. We've also done some simulations for this new strand mount installations that are getting more and more popular in the US. These are also examples of so-called small cells. On the right-hand side is an example of a simulation we did inside a box at a stadium. The image on the left, with the floating persons, was created to find out what the lowest mounting height could be for some planned lamp pole installations. The one above that was part of the same study, and a different combination of antenna models was used.
So let's go through the demo, and then we can answer all of the questions that you guys might have. So this tower, case study C, is also an actual site that was built incorrectly. So to explain that, I just need to open something here. So let's have a look at the scope of works. So I removed everything that could be sensitive information, but what you can get from this is someone decided to place the 5G antennas below with the rest of the antennas where there were open spaces. Some other views of the scope of work looked like this. Not a lot of effort was put in here with the planning, I guess, but you get the idea that someone decided we will add the antennas at the bottom because there's an open space. In our tool, so I've already opened this base station in our tool. And before I continue, let me just hide these lobe imprints to give you a better idea. So this is more than one operator. There's actually 4 operators. The operator whose scope of work document I just shown you has decided to place these antennas below, just above the crow's nest, as shown there. It is possible to walk around on this rooftop, and this is antennas of another operator. So what we want to know is it compliant for them if they install the antennas over here? So that's why we have underscore planned means this is what they decided to where they decided to do the installation. So if I run this, well, this simulation is already run, but if I put on the plumes, you can see clearly at the bottom here that this 5G plume goes all the way down to this rooftop. Now, this is not very useful. It looks nice, and you can see where all of the power is emitted, but to really see where the accessible areas are, we use our lobe imprint functionality, which means if this zone is less than 6 foot above this roof, then it should make the roof a certain color, like for instance, yellow. So what I'll do here is I'll just show these lobe imprints and then hide the plumes again. So what you see over here is accessible areas. So in other words, if someone would climb up, so I'll take my little guy here. If this guy would walk around, the moment he goes over this yellow line, he will be overexposed. Now, how do we resolve this problem? Well, you can probably move the antennas over there, but I would say if the wind loading permits it, it would be better just to move them up to the top. So that is exactly what we proposed. So in this case, I will disable the planned ones and enable the proposed ones. like I'm doing now. And then we run the simulation again. So then again, let me just also show them. So now the proposed positions is here at the top. It looks like they're floating in the air, but I'm sure there's a bracket there. All right, so in this case, the proposal was to move the antennas to the top. And now it's very easy. Now we can just check if it is compliant or not. So we'll do the simulation again. We'll run the simulation using IGNIRP. And it's taking into account all the emitters on the entire base station. And then we'll see if the site's compliant or not. Why is it taking so long?
It's because it's a demonstration. It always takes long when it's a demonstration.
Maybe while we
this
wait
morning
for
it
that,
was a lot quicker on my colleague's computer.
what I can maybe I can highlight a few additional things that
Sure.
while we're looking at this. So what happens here when we run the simulation? We make a tetrahedral mesh of the volume around the area here. And then we calculate the electromagnetic field at any point on that mesh. And then what we do is we systematically grow that tetrahedral mesh outwards and refine it as we go along. So it's a form of adaptive meshing, we call it, to cleverly obtain where the exclusion zone that you're seeing now here is. So we don't discretize the entire volume very finely and calculate it. We have an adaptive mesh technology. And what we also include there is a form of optimization. Obviously, I think in this particular case, which takes a long time, is the fact that you have quite a few radiating antennas there. So if you can see, I can't really, 1, 2, 3, there's almost 10 or 11 at various power levels. So also the power level of the antenna also determines how far this three-dimensional exclusion zone is now. But it's all things that we are also continually optimizing with our IXUS releases. We have about 2 releases a year. In our next release, we've got some GPU acceleration planned as well. But yeah, I'll hand over to Johan again, seeing that we've got the results here.
Yes, so all I can mention is that very clearly our problem is solved. The 5G antennas are at the top, and this guy is completely safe standing here on the roof. I don't know why he would be standing there, but he's very safe now. Just to give you a little bit of an idea of, so if you look at these plumes, it's sort of difficult to work with. I mean, it's difficult for people to understand that if you put it in a report, a lot of people don't understand it, or they have difficulty understanding the 3D aspects of what we were showing them. So what I prefer to do is to show them, firstly, those lobe imprints that I showed earlier is very useful, but that's a bit more useful for us to know where the accessible areas are. If you want to show something to the public, it's a much better idea to add something like this. So let's add a environmental slice over here, and then I'll put it on 6 foot. You can't see the settings now, it's in my other screen, but I just want to show you the results. So if I calculate the the limits on this plane, then you can see it looks like that. So now in this case, if I put on the legend, you can see 0 to 5 is this blue area. Sorry, white area. And then from 5 to 20 is this green area, and then below 100 is there. So the maximum is still over here somewhere. So if I switch on the maximum, then I'll probably see it pointing to a point over there. So there is the maximum for percentage of IGNOR public. 24.85% over there is the maximum on this rooftop, according to our calculations. So if you show something like this to people, it's easier for them to understand, and especially if you add some, I think there should be like stuff like this. So you can even add just hide the geometry in this case. So you can add like a Google Earth picture to show them where the areas are if they don't understand the 3D model. Or there's lots of ways that you can show where the areas are. Okay, so I think that solves our problem. In this case, what we would do next is, firstly, on the right-hand side, we'll create some pictures. So if I click on there, this is it's almost like in other CAD programs, you get these tabs of different views, but we created pictures like this. So it's also something that you can move around, and you can add comments and dimensioning and whatever you need to do. So if I want to add the length of the building, for instance, I can add that, and this directly goes into the report. So anything that comes up in on this area goes into the report automatically. And my default view is still there. Okay, so going forward, you would create pictures, export, and from there automatically generate the report. Okay, so let's go back to our slides. And
in terms of compliance, beamforming is the only influencing factor that discerns 5G from previous generations. Adding your compliance step early in the workflow saves money, and you have to keep an eye on the mounting heights of your 5G antennas. Thank you for joining.